right, let's get started. So like I mentioned, we're just going to lecture today, so no quiz this week. So hopefully we can get through all of these solution chapters. So I'll probably try to go a little quickly so we can get to calculation parts. And so basically, we're just kind of starting off with what is a solution. And I think most people kind of know what a solution is. We could mix table salt into water and it disappears, becomes homogeneous. And of course, many of us drink many solutions, right? Gatorade or whatever refreshing electrolyte drink. We work with a lot of solutions in lab, right? Everything from the dropper bottle is usually some sort of aqueous solution. And so, okay, homogeneous mixtures are called solutions. And then the minor component of our solution is the solute. So this is usually, right, a solid that gets dissolved, right, again into water if we're talking aqueous for our purposes. It could also be a liquid, right, that you dilute, especially like organics. And then our major component is called the solvent. Again, right, in CHEM, we mainly use water as our solvent, but if you move on to organic chemistry, there's many other solvents that can be used. So I'll just name a few solvents, again, like nowhere near an exhaustive list. Ether, benzene, toluene. And we could go on and on. Even CO2 could be used as a solvent. But anyways, so whatever is doing the dissolving. And so now let's look at other kind of mixtures. And so a colloidal mixture is just defined when we have essentially nanoparticles in solution, so just very small uniform particles. And so they are small enough to scatter light. And so it can make the colloidal mixture appear cloudy or opaque, or sometimes if you hold it up to the light, you can see like all the little crystals kind of shine in solution. But then you're probably familiar with colloidal mixtures without even knowing it. So fog and mist and clouds, so those are all colloidal mixtures. And again, you're kind of thinking about how the water particles, when it's foggy, right, they're all dispersed in the air, and then of course they also reflect light randomly. So you see again the Tyndall effect of dispersing the light with fog. You can have gas and solids, kind of like dust or smoke. So you probably have seen this. The sun's coming in the window, maybe you smack the couch, right, a bunch of dust particles fly up. So that's kind of the Tyndall effect as well. Or if you smoke, right, you blow out your smoke cloud into the light, and again, you can see, right, all the little particles reflecting in the light there. And so then other mixtures, so liquid gas, that would be like whipped cream, shaving cream, liquid-liquid mixture. So of course, paints are going to be involved in that, and obviously a lot of chemical compounds are used in paint colorings. That's a whole science. Liquid solid, so again more paint pigments, inks, and other mixtures. Solid gas, so that'd be like a pumice stone. Solid liquid, so gelatin or cheese. Again, just kind of thinking about how those form. And then solid, so thinking of mixtures like colored gemstones or ruby, so all the little impurities in minerals that make it colored. And so then this touches on how things dissolve. And so the most important saying is this like dissolves like saying. And so this goes back to polarity. And so basically if two things are nonpolar, so nonpolar dissolves nonpolar, And so with this example, so let's say you spill like a bunch of oil on the floor. Usually people go for hexane, but like I mentioned, hexane is toxic, so you'd want to grab the pentane or the heptane. So you just need either 5 or 7 carbons, so not 6. And so hexane and oil are of course miscible, right? So again, hexane or pentane, any of these hydrocarbons have these long chains, and then oils, right, are also just long, fatty hydrocarbon chains. So very similar, right? So both essentially nonpolar, so they dissolve or are miscible. And then, so obviously, things like water. So of course, we've mentioned that water is very polar. And so it can, of course, dissolve crystals or ionic compounds like we've seen. Or, of course, any other thing with hydrogen bonding or something that's polar. So I'll put there salts. And so this is also why organic compounds are like not soluble in water. So that can also go into like different forms of drugs too. So like drugs, they'll try to make it as the salt, so then it's going to be soluble when you take it. And so then this just goes through that in more detail. And so basically when you're dissolving something, you're trying to see if the attractive forces can overcome our solute-solute interactions. So again, you can imagine like a sodium chloride crystal, and then your water comes along to disrupt those electrostatic interactions there. And so then the attractive forces, if they're stronger than, right, the electrostatic interactions of our solute-solute, then they can dissolve. And so it won't go over this too much. We've seen this, right, with the polarity. I think I've brought these out before, but I brought them out, you know, again, so you can kind of play with the polarity and how it dissolves. So I'll leave this up front so you can play with that. So again, like we've mentioned, negative charge attracts our cation. So sodium, right, positive can attract our anion. So chloride or whatever, and again, right, allows for the dissolving of our sodium chloride crystal as it disrupts this sodium chloride interaction. And so again, we've seen this, kind of going quickly through this now. And so I'm going to save the electrolyte demo. I'll do another one next week, both in the interest of time, but also so we can see the strong acid, weak acid base connection. And so like I said, we'll hang on to this. We've kind of touched on this. So like we said, anything that can conduct ions are generally electrolytes. So these tend to be your ionic compounds. And later, like we mentioned, coming next week, this is also going to be strong acids and to some extent weak acids. But again, we'll look at the how and the why more next week. And then anything that's a non-electrolyte, these tend to be our molecules, right, our covalent compounds, and those do not dissociate. So they have sugar there is a good example. I'm again thinking of like common drugs, right, like aspirin, small molecules, or any other, right, pharmaceuticals. So all of those would be non-electrolytes, unless, like I mentioned, they made the salt form of the medication. And so again, we see that the interactions, so again, right, they have to overcome the solute-solute interactions. And so obviously, sugar and water, so more difficult to dissolve. So sugar still has, right, some OH bonds at least in it, but as you probably know from experience, right, you really have to kind of stir the sugar in there, so giving it a lot of kinetic energy. Or that's where people make those simple syrups, right, so that you can have your concentrated sugar solution. All right, so electrolytes, like I said, we'll look into this more deeply with the strong and weak acids. So this is the weak electrolytes. Again, the partial dissociation, so that's going to be weak acids, which we'll get into more next week. Blah, 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 so we'll kind of skip. So like I said, I'll bring the demo that shows this next week. So we want to compare acetic acid to a strong acid. And all right, so now we have a couple of rules now. So now this goes into solubility. So kind of now what drops out of solution. And so this goes back to your precipitation lab, and double displacement reactions is what we can think about. And so we kind of have to just accept some of these rules essentially. And so we kind of, we gave the why, but again, we're not like delving into each one in depth. And so obviously, right, we mentioned that we have to overcome those solute-solute interactions. And so now we have this statement, right, so not all ionic compounds dissolve in water. And so one example is silver chloride, and I believe we saw this one in lab. And again, right, we're not really getting the why this happens, but obviously whatever electrostatic forces are holding these together are strong, such that the water has a difficulty overcoming it. And then we're also not really quantifying it that deeply either. So at our level, right, we just want to say that something dissolves or doesn't dissolve. Let's see if I can pull up this. I don't like using my personal computer. So let's pull up silver chloride for a second. And so we're going to learn some kind of rules, but again, they're kind of general guidelines. And so if you actually want to get a deeper understanding and how you quantify it, you can take the 200 level series. But basically, it's kind of related to these two factors here. So there's different ways of reporting it. But basically, right, at some point there's a judgment call as to what is soluble and insoluble. And so you can roughly see where the rules come from. And so of course this has pretty low solubility of only 520 micrograms in 100 grams of water at 50 degrees Celsius. So not very soluble. And again, right, this tells you more information. And if you took the next level class, you could learn how to quantify that. So that's, again, the scientific backing behind these rules that we'll just kind of accept. And then, so again, we'll look at these kind of general rules. And so we have our terms of soluble if it dissolves in water, and then again, generally insoluble if it does not. And so again, just mentioning differences in solubilities. And so like it mentions here, right, we can't always predict. There's a few factors like electrostatic forces and how close they are together. But, right, we'd have to do an experiment. And like I mentioned, right, it's better to look back at the data too if you're actually trying to get a quantification, because, I mean, this can get into like water chemistry and how they purify water and different, all sorts of different detailed things. So for our purposes, these are the solubility rules. And so if you were to Google solubility rules as well on the internet, you'd find pretty similar tables. And so, I mean, I like this one just because of how it's laid out, but again, feel free to find another resource online. They should all be pretty similar. And so, kind of the key points is we have our alkali metals here, at least most of them, and then ammonium. So lithium, sodium, potassium, and ammonium. So these are always soluble, so notice those don't have any exceptions. And then if we look at nitrates and acetates, so remember this is acetate here, and acetate is again that organic one that's written in a bunch of funny ways. So those are always soluble, and you can think of, right, silver nitrate as an example, so that's given to you in a bottle during lab. And then we have, so chlorides, bromides, iodides, they have a few exceptions. So again, ones we've seen, so silver, and then we don't generally work with these since they're too heavy of metals. So right, mercury and lead, so those are considered pretty toxic, but also make insoluble products. And so again, right, those tend to come out of solution. I think we've seen some of those. And then sulfates, if you look at these rules, sometimes I think that's where you find some discrepancies. So it says when sulfate is paired with strontium, barium, lead, silver, or calcium, it's insoluble. But again, it's like varying degrees of insolubility. And so sometimes I see rules that like disagree, or they have like, there's discrepancies on the sulfates. And again, all that goes back to is the actual solubility, right? So it depends kind of what you're doing if you actually want to quantify it. And so looking at calcium sulfate, so if you just kind of compare, again, the solubility, so you can just see, relatively speaking, you know, it's more soluble than our silver chloride, so now 2.63 grams in a liter at 25 degrees Celsius, and it has these KSP values. So again, right, that gives you some context and why you might get discrepancies. But again, those are generally considered insoluble. And then the bottom half here is compounds that are generally insoluble minus a few exceptions. So hydroxide, sulfides are again usually insoluble unless they're paired with the following. So again, obviously if it's paired with the lithium, sodium, potassium, and ammonium, those are always soluble. And then again, right, we have our weird ones, so calcium, strontium, barium. So sulfides and hydroxides are both slightly soluble, so again, you might expect discrepancies as well when you look these up. And then carbonate phosphates, generally insoluble. Again, I think we saw that with some of those calcium tests when you made precipitates of calcium carbonate and phosphate that were insoluble to test for compounds. All right, let's do a quick practice. So I'll try to zoom out so you can see the rules and the problem. So take a minute or so and figure out whether it's soluble or insoluble based off of those basic rules there. So what do we predict for lead chloride? Soluble or insoluble? Insoluble, so good, right? You'll get your chloride rules, but then lead is one of our exceptions. So insoluble, or again, we'd expect it to make a solid product in our double displacement. What about copper chloride? So soluble, so copper is not listed there. And so again, right, that would be kind of AQ in solution. And I'm pretty sure we've worked with bottles of copper chloride in lab. What about calcium nitrate? So soluble, so again, nitrates are always soluble. And then barium sulfate. Oh, check that one. So most sulfates are soluble except, so then barium is one of our exceptions, so insoluble. So probably make a little solid there. Questions on this? So again, this will help you understand the double displacement reactions a little bit better. And again, right, predicting what your product would be, aka, right, whatever is forming the solid. So that's again what drives the double displacement. And so then we just want to look at some temperature dependence of solubility. And so I think most people have a general sense of this, right? And so it's generally given that solubility increases when the temperature increases. And so again, right, people have probably done that to dissolve sugar or whatever you're trying to dissolve, make a solution of something. And so we're just kind of appreciating the curves here. Again, we're not really getting into the why and the what's going on. Obviously, we do want to point out there is some exception of the cerium sulfate. Again, I'm not sure why that is. We'd have to delve into the papers. But, you know, something about heating it must not be favorable, right, for those solvent interactions or something. So that would be my prediction, but again, a rare exception. So obviously heating things usually makes things dissolve. And then if we think about gases dissolving though, so gases are the opposite of solids. So you might want to write that down. So meaning that their solubility tends to decrease as the temperature increases. And so this is because, right, our gases tend to be nonpolar, especially compared to, right, like water that they're dissolved in. And so again, right, our solubility then decreases as our temperature increases. And so that kind of makes sense for these weird gas liquid solutions. So again, if you're heating it up, then it causes our gases to escape, right, especially as they get more energy. And again, they have pretty weak interactions to begin with, so that's what it's saying here. And so I like the picture. This kind of helps us see it and, you know, understand kind of what's going on. Especially, right, if you pour out a cold soda, sometimes I find like cold soda is not as satisfying because they don't get all like fizzy, right, like the warm soda. But of course, that's just because, right, there's more gas dissolved in there. As opposed to if you crack open a warm soda, it's going to be more fizzy as, again, those gas bubbles escape. And so then this is asking, right, how can we make a supersaturated solution, basically? And so this is where you kind of played with the sodium acetate, right, to make your sodium acetate supersaturated. And then a lot of you notice how you had to kind of pour it out and manipulate it for it to recrystallize back out. And so again, that's our supersaturated solution when we dissolve more than kind of the standard amount. Again, right, simple syrups are an example of supersaturated solutions. And so these solutions can also become unstable and lose all the solute above saturation. So right, you can shake a carbonated beverage and then that causes it to fizz out. This kind of gets into like the Mentos thing too, and why it makes like the diet soda fizz out. So same thing, it makes it kind of unstable, and I think the science behind it is like the Mentos provides a weird nucleation site, especially for the diet soda, because you also have like the aspartame in the mix too. So that just makes it unstable and then releases all the gas. So same sort of concept. All right, so this equation, getting into the math, this isn't as important as the math that we're trying to get to, but this we can just appreciate how we derive it. And this is just basically like how to can soda, if you wanted to can soda. And so, okay, basically you figure out what pressure you want, and then you have to look up the Henry's law constant for every gas, right? So every gas has this constant. But then I always say, let your constant dictate your formula. And so based off of our formula, right, dimensional analysis, it's giving us a concentration of CO2. So we have this basically, right, for every 1 atm of pressure, we get 3.4 times 10 to the negative 2 moles of our molarity of CO2 dissolved in our solution. So we're just, again, it's just a way to figure out how much pressure you need to can your soda under to achieve your desired CO2 or any gas, right, amount. So obviously we're focusing on CO2 since most sodas are CO2, obviously, right? There's like those nitrogen brews or whatever for coffee. All right, so now this gets into kind of the math that we want to focus on in this chapter. So obviously these solutions have variable compositions. You saw that just today, right? You saw a 0.1 molar NaOH solution. And so to describe a solution, we have to have their component and their amounts. And so we have these kind of vague terms, dilute and concentrated. I like to think that dilute tends to be less than 3 molar, and concentrated would be greater than this. Again, just kind of a very rough guideline. And then our concentration is, of course, our amount. And so this is what's important. And so this is kind of our overview cheat sheet, I would call it, of all our formulas, and then we'll kind of go through more slowly now how to deal with all of these and do some calculations as promised. And so again, and this is something, right, that the stockroom too has to do like all day, every day, is figure out what solutions they need to make, how much, right, depending on what's going on. And so the first one we see here is molarity. So this is the most common unit used in chemistry. Again, right, we see it all the time when we walk into lab with the big M. That's what we're talking about. And so you might want to write this formula down. And so it's the moles of solute over your volume of solution in liters. So again, that's the most common one that you'll use all the time that we'll see. And then, like I said, we'll go through examples. We're just kind of hitting the other ones. So now you have molality, which again only varies by a little L here. And so some people think that, well, not some people think, but molality is considered to be more accurate because volume slightly fluctuates with temperature. So if you were being like really, really rigorous, you might want to use molality, since this is moles per kilogram of solvent. And so of course, right, water has a density of 1, so it doesn't really matter, but like I said, if you're worried about small amounts of variation due to temperature, you might want to use molality. That being said, I never see molality, at least used in my practice. Perhaps if you're in another analytical field. And then we've looked at mole fraction with our partial pressure chapter, and it's back. So again, amount of solute, or whatever our minor component is in moles, over our total amount of moles. So in this case, right, it would be solute and solvent, or again, right, the total amount of moles in your mixture. And then we can, of course, take that to a percent. And then there's also other ways to report it. So we have a parts by mass. And so this could be, sometimes you see this abbreviated like gram per gram, right, like a percentage potentially. So that goes into percent by mass. You could also have, so going along with this, like part per volume, right? So it could be a gram per volume solution. I think that was given to you in lab, so like I said, we can look at some of your calculations. And then we'll look at parts per million and parts per billion and how to kind of deal with this. So of course, this is more used in like water chemistry and reporting impurities, right? Like looking for trace metals or other volatile organics. So obviously you don't want those in your water. And so you'd be looking at parts per million or parts per billion detection levels. All right, so now we'll keep getting into kind of the math of it. And so again, right, how to prepare a solution. So you have to know how much and what's the concentration. And again, that varies on your prep. And so again, this is what our stockroom does for us. So again, give them a big thank you when you think about it, right? A lot of math, a lot of preparation involved. And so we'll have to figure out, again, generally based upon the volume, figure out the mass of the solute we need, again, based off of the anticipated volume of solution. And then again, using whatever unit we're given in. So this one is a weight per weight, right? So that would be like a gram per gram, so by mass. So if it's 5% by mass, and of course, easiest way to treat percentages is think about it as a part over 100. So okay, 5% by mass, literally what is that saying? Okay, 5 grams of solute for every 100 grams of solution. So just pay attention, of course, right, to what they're giving you the concentration in. And so now let's kind of look at how you would physically do it as well. And so what do we want to do here? So it says we want to prepare a 1 molar sodium chloride solution. And so again, 1 molar would be 1 mole per liter there. And so it looks like we want to prepare a liter of it. And so we see how they weighed out 1 mole of sodium chloride. And then to properly prepare it, so we have here, this is a volumetric flask. And they are used to measure literally one value. So they have like one line there. So they're super accurate to whatever points. So right, you can look at your volumetric and they have some sort of tolerance there. And so this would be a 1 liter volumetric. And so then you first weigh out your solute and then add enough water till it's dissolved. So like I usually say about 3/4, you know, kind of shake it up, get it all homogeneous looking. And then very slowly, you want to take it up to the line. And of course you have to get at eye level, go drop by drop, because you don't want to go over, right? Because now it's inaccurate and you'd have to start over. And then get it to the line, and then you can kind of shake it up. It's not shown in this illustration, but usually these volumetrics have some sort of ground glass stopper here, so then you can put a stopper and then shake it, invert it so it gets all mixed. All right, so that's how you physically prepare it. So again, we're still kind of looking at the math though of all the different ways. So now we can look in more detail. So again, molarity is the most common one, defined as moles per solute, moles of solute per 1 liter of solution. So if we have a 2 molar solution, right, we have 2 moles of sugar in 1 liter. And then of course, you could also use like a proportion to help you with this part. So think of things in ratios, right? So 2 molar solution means we have 2 moles, 1 liter, or right, 4 moles, and 2 liter, etc. So right, just kind of think of it as proportion as well, if that helps. So then, like I mentioned, molality, more accurate, but I don't know why it's not used so much in practice. So defined as moles per kilogram of solvent. And so like it mentions, does not vary with temperature. So more accurate. So again, moles per kilogram. So of course, if it's water, you don't have to worry too much, but otherwise you'll have to either be given the amount in kilograms or take density into account. And so then these parts generally aren't too hard, but like I mentioned, you just have to kind of read what you're being fed, because they can be given, like we mentioned, in mass or volume. And so generally in the same units, so hopefully if it's mass per mass, right, it should be grams per gram or pounds per pound. Same thing with volume. And so again, 9% solution by mass, or 0.9% by mass, excuse me, is 0.9 grams of solute and 100 grams. And again, right, I would just set up a proportion so that can help you with the calculations a lot. And so now we get into parts per million. So of course this means parts of solute for every 1 million parts. And so if we are saying this, then a solution that is 36 parts per million has 36 milliliters of solute in 1 million milliliters of solution. And this is fine enough, but I actually don't find this too intuitive. And I much prefer to think about it like so. And so again, right, we mentioned that it's 1 over 1 times 10 to the 6 in parts per million. So we can think about that and convert it to milligrams per kilogram. So milligrams of solute. And so if we think about milligrams, so milligrams is 10 to the negative 3. Kilograms is 10 to the 3rd. And so that gives us our 10 to the 6 factor of difference there. So I much prefer that. So again, milligrams per kilogram gives us parts per million. So that's a good conversion factor there. So again, I would kind of highlight that. And then, so parts per billion, right, pretty similar, except now it's billion. So 1 over 1 times 10 to the 9th, right, parts in a billion. And so again, I don't find that very intuitive to think about. And so it's easier, at least for me, if I convert our solute to micrograms. So micrograms is, of course, 1 times 10 to the negative 6. And then if we take it over kilograms, so 1 times 10 to the 3rd, that gives us, right, our billion factor difference there of 10 to the 9. Does that make sense there with the million and the billion, kind of how to treat that? So again, proportions are your friends for these. And so again, we mentioned mole fraction kind of with our partial pressures. I should kind of put that right, partial pressures. So we can think back to this as well. And again, we just want to figure out the moles of whatever substance we're interested in. So substance A, or right, tends to be our solute, over our total moles. So our solute plus solvent in this case. And then, like we mentioned before, obviously you can multiply it by 100 and take it to a percentage. Yes, we'll finish up this C1B1, and then I think that'll be a good spot for a break, and then we can practice some of this. What do we have left in here? All right, so we have diluting. And so again, this is something that the stockroom does all day, every day. And so this is just the most general form of the formula. So whatever your first concentration is times your initial volume equals your new concentration times whatever desired volume. And so what's nice about this general formula, right, is it doesn't matter what the units are as long as they match, right? So we can be in gallons, we can be in any concentration. So I'll say units don't matter. Right, percentages, weight per volume, whatever. So that's really nice. And so you often see this formula, M1B1 equals M2B2. And this is obviously just, right, specific for molarity. But I really don't see the point in this formula because, like I said, it applies for everything. So it's just a relationship, so it doesn't matter what our concentration or volume are in. And so now we can see, again, what the stockroom might do for us. So again, right, sometimes you prepare either these stock solutions or you purchase them, especially like the acid, right, that always comes as like a 12 molar stock solution. And so let's say you want to dilute it. And so, right, it kind of depends what you're given, what your C1B1 is. It doesn't matter, right, just as long as you pair the correct things. And so let's just say for a lab, right, we need 3 liters now of a 0.5 molar calcium chloride solution. And we happen to have a 10 molar stock solution. And so let's figure out the math first before we kind of follow along with what they did physically. So again, we'll set up our C1B1. So our nice formula And so again, I'm just going to call these C1 and V1 since that's just one set of conditions. So 3 liters, 0.5 molar equals, so we're trying to figure out, right, how much of our stock solution do we need? So formally V2, but and so now I'm just going to punch this into our calculator. So 3 times 0.5 divided by 10. And so, right, again, this was in liters based off of this. So 0.15 liters or 150 milliliters of, again, our stock solution. And so now we can see what happens and how this would happen physically. So now that we've done the calculations, then the stock room, again, kind of as best as you can, so it depends on what equipment you have available. So ideally a pretty accurate graduated cylinder. You could also use like a volumetric, right? A volumetric flask would also be appropriate, again, if you had the correct amount of 150. So again, it depends what equipment you have laying around. So then you measure the appropriate amount, pour it into our volumetric. And so notice, right, this would have to be a 3-liter volumetric flask, or again, unless they prepared it in different portions. And then just like before, you may want to dilute it a little bit, shake it around, and then again take it up right to the line, and then you can again dilute it, mix it, shake it, make sure it's all homogeneous. And then then the lab is ready to go for y'all. All right, let's take a little break there, and then we can come back and work on this problem. All right, so take another minute or so to calculate it if you didn't already. I saw a few people going through it, and then we'll work through it together. So I've sketched out the work here. So again, just using our C1V1 equals C2V2. And then again, just plugging into our formula. So 0.2 times 15, and then divided by 3. So then we all get 1 liter. And then what's important is to kind of understand, again, what this is saying. Because it's saying to what volume should you dilute this. So then this is saying, like, if we were preparing it in, like, physically in a volumetric flask, we would take this 0.2 liters, right, put it in our volumetric that's appropriate. So if we calculated 1 liter, then we'd put it in a 1 liter volumetric, and then again add water until we're at that 1 liter line. But then that being said, if you were asked, like, how much water should you add, then you'd want to subtract, right, the 1 liter minus what you already had initially. So I think that's the only, like, kind of tricky part, is sometimes, especially, so if we do the quiz next week, that's generally planned, there's like a question and it asks, like, how much needs to be added. And so that's where you want to subtract it. But this one asks, right, to what volume? So asking the total volume. So just kind of watch that wording there. All right, so I'll try to move through this kind of quickly so that, like I said, we can look at the other calculations. So I don't want to neglect this, but I don't think we'll do too much calculations with this in here. So again, right, let the constants dictate your formula. So basically, everything has a freezing point depression proportionality constant, Kf, and they should be given in units of degrees Celsius per, and this is the, like, one of the few times you see molality, right? So it's that little m. So again, moles per kilogram of solvent. So molality. So maybe highlight that. That's a little weird. That being said, right, maybe it could be given in other units if you were to just look this up on the internet. So just always watch the units that it's given in. And then what we want to appreciate is this curve here. So again, we don't want to get too bogged down by it, but okay, we're looking at our pure solvent, and then we're looking right now at our solid liquid line. And so if we have a solution, right, what tends to happen is if we have a solution with different particles, right, it disrupts those intermolecular forces. And so to melt then, or to freeze something, so to get it to solid, right, we would have to get it at a lower temperature. And so that's where you get the phrase freezing point depression. And so now you can think about, well, this is why they salt the roads. So freezing point depression lowers the freezing point of water, obviously. So it's at 0. You salt the roads, and then it's lower than that. And of course, we can now quantify that and quantify the temperature difference based off of this KF. So again, blah, 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 salt disrupts the equilibrium. And so again, you have to slow it down more. So then this is an example of these different values. And so first we're just looking at, again, our freezing here. So our freezing melting line. And so this is the solvent. And again, right, it lists all of these solvents. Most of the time we're looking at water though. And then it just gives us our normal freezing point that we can, of course, see how much lower it is. All right, so try this one for a second, and then just watch what it's trying to tell you. So highlight the key word, and then see if you can plug it in based off of our KF here. So in the interest of time, I'll just start going over it. So again, right, go off of your KF here. And so our formulas, our change in temperature is equal to, right, our KF times our molality. Again, right, we can just get that from our units here. And then again, I was trying to say don't overthink it, because we have this ethylene glycol, but this is our solute, and so aqueous means that H2O is our solvent. So then we want to look at water and the KF there. And so now I'm going to plug this in, so 1.86 for the KF. And then they gave us the molality, so times 1.7 for, again, our molality. So we didn't have to calculate anything there. And then, right, again, see how once you multiply these two together, that gives you your degrees Celsius, which is, again, how much it is lowered by. So we should have a change in temperature of about 3.16 degrees. And then, of course, we subtracted from our normal freezing point, so negative 3.6 degrees Celsius. Oh, 1.6, sorry. So again, not too difficult. And so same thing, or pretty similar, except for boiling point. Now elevation, And so the important part is this is for only the addition of a non-volatile solute, aka like a solid, right? So if you were to add like something else that was volatile, like let's say you added acetone to water, acetone's pretty volatile, so it may not have the same effect, but again, that's kind of an aside for another course. So we're just focusing on these solid solutions. And so this is always like, I call it the great pasta debate, like should you add salt to your pasta water, you know, beforehand or after? And there's always a whole bunch of opinions on that. But some people say, right, so if you add the salt before, then it's going to have to get to a higher temperature technically to boil. And some people think that that's a good thing to boil a pasta. Some people think that's a bad thing. I don't know. There's so many opinions. But that's where you can join the great pasta water debate. And so similarly, right, you would just refer to the KB, and again, right, multiply it by the molality in this case to give us our change in temperature, this time increasing. So again, boiling point elevation, freezing point depression, and again, this gives you your change in temperature. And so you'd be provided these on an exam or so. So let's try this problem. So what mass of ethylene glycol must you add to 1 kilogram of water to produce a solution that boils at 105 degrees Celsius? And let's get you the KB of water, so 0.1 or 0.512. So KB, H2O. So try that out. So how are we doing on this one? So we can at least set up, right, our change in temperature equals our KB times our molality, right? And so then we're given our change in temperature is 5 degrees Celsius. I gave you the KB from the chart of 0.512. So now we need to solve for the molality. So we can do that first. So divided by 0.512. So I get that we need a molality of 9.77 roughly. So again, that's moles per kilogram. And okay, they're saying, so what's the mass in grams? You must add to 1 kilogram of water. Okay, well this is nice, right? At least we're already set up in our ratio. So then I can say, well, I need about 9.77 moles of ethylene glycol. And so since we have moles, and so if it wasn't 1 kilogram, right, we could have set up a proportion, and that probably would have been the easiest approach. But again, it was a nice easy proportion. So now we have 9.77 moles. They did not give us the molecular weight. So right, we can kind of roughly add it up. So I'll just take some rounded numbers. So 12 times 2 plus 6 plus 32 for those 2 oxygens. So about 216 for the molecular weight, roughly. Again, you could look it up as well if you wanted to be more precise or use more decimal points. But roughly 216, and then times the amount of moles we said. So 9.77, again, just kind of rounding. So 2,100 grams there for our answer. Questions on that one? And then of course these problems are nice. You can always kind of plug it back in, right? Divide by 216, get back to moles, and then multiply by our KB, so everything checks out again. Questions on this one? So last bit of the chapter is, so it mentions osmosis. So this is just defined as the flow of solvent from a solution of low concentration into a solution of high concentration. So usually because there's some sort of semi-permeable membrane that allows water to flow through. And so here's just a visual representation. So we have our water molecules and then also some solute particles. And so now it's going to flow over to, from the diluted side to the more concentrated side to try to make the the concentrations the same. And so then if you were to try to prevent this, this would be defined as the osmotic pressure. And so this isn't necessarily so important, but we want to look at something that we haven't quite talked about. And it should have this little I factor here. And so let's talk about this I. And basically what this is saying is, how many particles does it make? And so it's clear if we look at this diagram or this chart as to what they mean. And so if we have, again, our non-electrolyte, again, sugar or aspirin, whatever. So if it does not dissociate, right, then obviously it's going to stay as 1. But now, if we look at sodium chloride, and let's just say we have, right, a 1 molar solution of sodium chloride. Well, once it disassociates, right, what you're saying is, well, I'm going to have 1 mole of sodium, and then I'm going to have 1 mole of chloride ions. So I have a total of 2 molar of ions in solution. And so, right, it's making more dissolved particles. And then this is just kind of saying, right, that maybe there's some sort of equilibrium, or it's not fully disassociated or something. It's not quite clear why this measured is off. But again, we're just going to go off of what we expect. So if we have a 1 molar solution of magnesium sulfate, again, we're saying that it disassociates into 1 molar of magnesium and a 1 molar solution of sulfate. So again, 2 molar total of ions. And so that's just continued. So again, magnesium chloride dissolves into 1 magnesium, 2 chlorines, so again, 3 molar of ions. Same thing, potassium sulfate. And again, right, iron chloride, just to emphasize that this pattern continues. So again, so in this case, we'd have 1 mole of our iron 3 and 3 moles of our chloride. And so again, some people may care about this, or again, it depends what you're looking at, or if you're trying to quantify total ions in solution. So one thing that you might notice, if you were to compare, if we were to do the light bulb experiment and do a 1 molar solution of sodium chloride versus a 1 molar solution of iron 3 chloride, I would expect this one to be brighter, right? Just because it has more ions in solution. And then other industries may care about this. I'll kind of put normality as an aside here. So this is a unit, we don't necessarily talk about it in here, obviously, but I've seen this used in industry, especially like Ericsson down the road, you know, that company that does like plating. So I don't know if you're familiar with like Ericsson, but they do like all sorts of either electroplating or chemical plating for helicopters and big manufacturing, all sorts of things. But they care about normality and how many ions are in their solutions total. So again, just something to think about if you go off into the world. So you may see normality, and that's what it's referring to. And then last little bit, so if some of you guys are in biology, you may have talked about this concept before. So we do want to know these terms. And so I'm used to the term isotonic. You might see isoosmotic in biology. Both of those just refer to that we have the same concentration both inside and outside of the cell, so there would be no net flow. And then we could have a hypertonic solution where we have a higher osmotic pressure outside the cell. And so with this one, I like to think about maybe you had, you know, a high sodium diet or something, and then your poor cells, if they're trying to, you know, get back to equilibrium, so they would be kind of shriveled up, obviously. And then a hypotonic solution, or hypoosmotic. So this one, I saw it in, like I said, I don't know if anybody is in a bio class where you talked about that, but I think y'all, if you did, you looked at a case study as to like those gallon challenges, or like it's either milk chugging or water chugging, so why those can become deadly. And so what happens if you drink too much water at once is, of course, you would end up with a hypotonic solution where the solution outside of the cell does not have a lot of electrolytes, And so then the water would go into your cells, and of course, in the most extreme cases, right, they can cause your cells to burst and then cause death. That's how people die from drinking water, which is kind of crazy to think about, but. All right, so now let's look at the math and just kind of continue practicing. Let's see, I did want to look at your lab, so let me see if I can pull up your lab. What do I do with your lab? Sorry, too many things. All right, so the first thing that I wanted to cover from your lab was some of these stoichiometry questions. So I had promised, I think this is 6 on the pre-lab, and then trying to get it not a microscopic size. And so now let's go through this one together. So it says if it takes 15.75 milliliters of a 0.1 molar sodium hydroxide solution to neutralize our vinegar sample, how much vinegar, because this is just acetic acid as vinegar, is in our sample? All right, so I'd probably write out an equation just so it's clear what's going on. So we have NaOH plus our acetic acid, which I'm just going to rewrite it as its structure, so it's not just a weird chew compound or nacho or whatever. And so then we react these two together to do neutralization. And so again, this is our acidic proton. So then we form HOH, so water obviously, and then we make sodium acetate, or what I always think looks like nacho kind of when they have it written. And so the whole point of this was to see that they're in a 1-to-1 ratio of NaOH to vinegar. So however many moles of NaOH it takes, right, that's that many moles of our vinegar. And so now we just want to use our molarity definition and dimensional analysis to convert this to moles. And so again, I'm just going to rewrite our molarity. So 0.1 molarity is moles per liter. And so then they tell us it takes 15 milliliters. So then I would convert this to liters, right? So 0.01575 liters of NaOH. So now we want to find moles. So you can see how this is going to cancel. So multiply by the amount. So again, in liters there. So liters cancels. We're going to be left with moles. So now let me plug it in. So 0.1 times 0.01575. And so then we get, right, that many moles, so 0.001575. And again, that's moles of NaOH. For completion's sake, we'll just show that they're in a 1-to-1 ratio. Right, so for every 1 mole of NaOH, it neutralizes 1 of our acid. So again, that's 0.001575 moles of acetic acid. And so now this should feel familiar. So most people are doing pretty well on the quizzes. I'll hand those back as well. And so again, moles. Now we need the molecular weight of acetic acid, which I want to say is about 60. I'm going to look it up because I feel a little lazy. Otherwise, we can add it. So 60. So acetic acid molecular weight is about 60.052 grams per mole. And so now we can figure out the mass that was in our sample. So 0.001575 moles times 60. So times 60. And so that gives us how many grams are in our original sample. So 0.0946 grams. So we haven't done too much, right? We just added one little extra layer of complication with our stoichiometry calculations with our molarity, right? But still the same basic principles. So then I wanted to do more problems, or actually, we'll do the post-lab questions next. And so I'll do 8, but I'll have to do 7 to do 8. And so this is pretty similar to what you'll do. If we need to do more calculations, we can. And so then the post lab asks you to kind of compare and repeat everything except we have sulfuric acid. And so one of the complications of the post lab is that this is a diprotic acid. So AKA it's going to take 2 equivalents of sodium hydroxide. So that's the first thing I'm going to do is write out our balanced equation. So now 2 equivalents of sodium hydroxide plus 1 equivalent of sulfuric gives us again 2 equivalents of water, and then sodium sulfate, which would be aqueous in solution. And then, so this is essentially the calculation you're going to do, again, for your lab. If you want to go over it, we can. But again, the only difference is this 2-to-1 ratio here. So let's go through this one, like I said, together for now. And so we want to find our moles of NaOH first. So right, we have that information because we're given volume, we're given concentration. So let's do that. So find moles of NaOH. So again, I'm going to rewrite this as moles per liter. And then we can multiply it by our volume in liters, so 0.0325 to give us moles. And so we can do mental math, so 0.00325 moles of NaOH. And then, like I said, the only difference is this is a 2-to-1 ratio. So when you're doing it for your lab, right, it'll be 1-to-1 Again, post lab's 2:1, so I will set up our ratio so we can see that. So again, if we have this many moles of NaOH were required, and we said we needed twice as many moles of sodium hydroxide as we did sulfuric acid. So now 0.00325 divided by 2. So that's our moles of sulfuric. So 0.001625 moles. And so then let's kind of look at where we're going. And so it asks us for a weight per volume percentage. And so luckily it is a weight per volume, and we are given volume here, right? So we just need to find our grams then, right? So that's what we're saying. So we want a gram per milliliter concentration. And so we're almost there. So again, let's convert this moles to grams then. So again, I'll look up the molecular weight of sulfuric acid. You could add it. And so our molecular weight, again, I just looked it up, so 98.079 grams per mole. So multiply that to get our total mass, right, just like before. So now that's mass of sulfuric acid in my sample. And so now we can do what it was asking. So again, I wanted this as a weight per volume percentage. And so we can literally just do that, right? So 0.159 grams per 3 milliliters. And so let's convert that to a percentage now. So divided by 3, and then times 100. Since again, I just wanted a percentage. So we get about a 5.31 weight per volume percent there. So like I mentioned, you'll do kind of the same thing for your lab, right? So going through, I think everybody got somewhere like 15 to 17 mils of NaOH, convert that to moles, 1-to-1 ratio, and that'll give you, again, your weight per volume. Let's see, let's look at I'm just trying to look at your homework really quickly to see what is difficult or not. So we might want to go through this. I think it's pretty straightforward, but we can always practice that. I do want to point out the N part. So this is, people sometimes have issues with this one. But what it's trying to get at is, again, those colligative properties. And so you have to figure out, right, how many particles are truly in each solution. So looking at this, and let me copy it over so I can write on it. Make a new page here. And so, right, it tells you to kind of rank them. So the first one is increasing vapor pressure. But before we even worry about how to rank them or anything, we need to figure out what their true molarities R. So does sucrose dissociate? Or how many particles does it dissociate into, we should say? Or does it? So sucrose, I guess I'm really asking what its Van Hoff factor is. So what do we say about sucrose? Does it dissociate? This is just sugar, right? So does sugar dissociate? So no, right? So again, it's a covalent compound. So Van Hoff factor would be 1. So it's still a 0.1 molar solution, is all we're trying to say. What about sodium chloride? So how many particles would it make in solution? It's its Van Hoff factor. So how many particles would you get from 1 sodium chloride? So did you do this times 2 already? So, yeah, so what we're trying to say is, right, it would dissociate into 2 particles. And so then you want to multiply, which I think some people were doing, right, multiply the 0.08 then times 2 to give you your effective molarity of 0.16. Does that make sense? And then, so for the last one, magnesium chloride, how many particles does it dissolve into? Yeah, 3. And so now times 3, but then this is still the lowest solution at 0.09 molarity. All right, so then increasing vapor pressure for 8. So basically, right now that we know how to rank them, so this is always the least particles, this is always the most, this is in the middle, and then we just have to look at our scenarios and then figure out kind of which way to flop them. And so it's asking for increasing vapor pressure, but remember, more particles means that lowers our vapor pressure, right? Again, boiling point elevation. So we have to take it to a higher temperature to get that same vapor pressure. So then the highest vapor pressure would be this solution, magnesium chloride, since it has the least particles. So highest vapor pressure, and then sucrose is in the middle, and then the lowest is sodium chloride, because again, boiling point elevation, so this has to be heated the most. Oh, so lowest vapor pressure. And then you just want to continue that for the rest of the homework as I lose the Jeopardy homework. So then, right, 9 would be similar. So we're just ranking them in increasing boiling point. So of course, now the sodium chloride has the highest boiling point. Sucrose is still in the middle. And then freezing point. So again, freezing point depression. So this will have the lowest, magnesium chloride the highest, and then osmotic pressure. So that goes back to, right, sodium chloride the highest, and this the least. So that's how to approach that one there. So we could kind of in these last few minutes, kind of look at 1 and 2. So 1 is pretty easy. So obviously we have our naphthalene dissolved in our chloroform. So liquid chloroform is of course not only a liquid, but is the major component. So then it's the solvent. And so then see if maybe in the last few minutes we can try to do 2, 3, and maybe 4 there. So how would you calculate molarity? How would you calculate weight volume percentage? What would be the easiest way to get number 4? So I'll let you try that for a few minutes. All right, so we're kind of running out of time, so I'll probably, again, just kind of quickly go over them so you can see how to do it. Again, just giving you a taste of all these calculations. And so again, right, we always just have to ask ourselves, what are they asking? So the first question, question 2, asks for molarity. And so again, that's going to be moles per liter. And so again, I'm just trying to do this quickly here to squeeze everything in. So obviously you can calculate naphthalene, or we can look it up. So in the interest of time, looking it up, so 128.74 grams per mole. And so again, if it wants molarity, let's find how many moles. So 10 grams divided by our molecular weight divided by our liters. So 0.5. So 10. And again, right, have your mole highway handy, whatever you need to kind of help you on track. And then divided by 0.5. And so then that gives us our answer, so 0.156 molarity. All right, so that's number 2. And then let's look at number 3 and 4 really quickly. I know we're almost out of time. But I just want to point out, right, again, do whatever makes sense. So first it asks for weight per volume concentration. Okay, well that's not too hard, right? Weight per volume, so we have 10 grams in 500 milliliters. We could do a weight per volume percentage. So again, 10 divided by 500. And so we have, so of course multiply it by 100 to get it as a percent. So about a 2% weight per volume. And then all I want to point out for 4 is we want to do it with the easiest method, right? So it says what volume has 2.7 grams. You could use this, but that's a lot more steps, right? Just set up your basic proportion. Well, if I have 10 grams and 500 liters, what's 2.7 over x, right? And then just cross multiply to solve. So 500 times 2.7 divided by our 10. So then we get, right, 135 milliliters. All right, so we're probably out of time, but again, that's kind of the trick, is like use your units, right? Kind of what do you know? What do you need to solve for? Mole highway, right? Just think, set yourself up. And again, right, molarity is just our moles per liter ratio. All right, so I do have your exam, so you can take it home and start working on it and whatnot, right? Take your time. So since it is a take-home exam, right, I expect you to show your work and everything. It would be nice if you had like simple explanations for the not free response, the multiple choice portion here. And then everything else is free response. So again, just show your work, show your work. There is a bonus question, so at some point I'll try to go over how to calculate it. Otherwise, you can attempt it. You can ask me for questions, for help if you have questions, especially because some of it, you know, is over the acid bases chapter. So just ask me for help if you need, and I'll push you in like the right direction. I would ask that you don't collaborate, right, with your classmates though on it. Obviously, you can ask them about general concepts. So if you find a question in the exam you don't understand, right, you can ask them, your friends, how you might approach it. But again, don't collaborate on the exam. Just ask me for help if you have issues. And then again, right, it's open resources, internet. I wouldn't ask ChatGPT for help, but that's probably too far. But again, right, everything else is fine, open notes. And like I said, you're more than welcome to ask me. And then I put it that it's due, so next Friday, ideally by 5 p.m. in the mailbox. I would just like them physically. If you can't do that for some reason, you know, just let me know. Worst case, you can always send me like a copy by photos or email, but I would prefer a physical copy at some point. So if you absolutely can't get it to me by next Friday, finals week would be okay as well. Any questions about the exam?
By mailbox, do you mean the mailboxes in the...
Yeah, on the third floor suite. So yeah, if you don't have it ready to me, you know, by like Wednesday, which I don't like expect you to, then yeah, you can just turn it into the mailbox. And like I said, it's 5 p.m. just because that's when they lock up there. But like I said, if you can't make the deadline, just let me know. I'm happy to be flexible, but I think I'll be okay with it being take home. All right, good luck with that. And again, just ask me questions if you need help, if you're stuck on stuff. Otherwise, have a good weekend. And yeah, lab practicum next week. We're almost there. Thank you.